everyone. This is the start of the 7.3 worksheet. And what we're going to be doing is using a piece of string and a compass to complete a couple tasks. So the first thing, we're going to take our compass and construct a circle that has a radius that's equal to the length of the piece of string. Okay, so on a separate sheet of paper, I've got this piece of string. It doesn't matter what length string you have. And what I'm going to do is just go ahead and mark the ends. And then this right here is going to be the center of the circle. And then the other mark is going to represent where the circumference is going to go. So taking the compass, I'm going to go ahead and create a circle. All right, so then the next part of the question says we're going to construct an angle whose vertex is at the center of your circle and that cuts off an arc that has the length of your piece of string. So what that means is we're going to go back to our circle. I'm going to go ahead and just draw one line to start with. So from the center to the circumference. And then I'm going to take this piece of string, the same one that you used to create your circle, and I'm going to put it on the circumference. And so there's one end of that line, and then I'm going to mark off the other end of this line. And then I'm going to connect those dots. Okay, and this right here gives us an angle. Okay, and I know on the worksheet it says to compare the openness of your angle with that of your classmates, and what do you notice? So I know most of you are watching this video alone, so I'm just going to go ahead and show you some other circles. So here's one circle, here's another circle, here's a different circle, there's a different size circle. And the key thing is, what do you notice about that pie piece? And the thing that you should have noticed is that they all have the same openness. So regardless of the radius size, they have the same openness. All right, next part, so part C. So use your piece of string to create an angle that cuts off an arc that measures 3 radius lengths, and then again compare the openness of your angle with that of your classmates. So what we're going to do is go back to this right here, and we're going to mark off 3 of those. So one of them has already been done. Here's the second. And then there is the third. And so if I mark this off, going from that first line to this terminal line, your circle should have ended up very similar to mine, where it's just shy of the halfway mark. So if this is the halfway mark, meaning exactly halfway across the circle, it should be just a little bit short of that. So again, if we measured 3 of these pieces of string, we will still have the same openness. All right, and then for part D, we're going to use the piece of string or radius length as a unit of measure. How many radius lengths rotate along the circumference of your circle? Okay, so we've already got 3 marked off, so I'm going to go ahead and start marking them. So here's 1, 2, 3, and then we're going to keep going. So this marks 4, and we've got 5, and we've got 6, and then we don't have the rest of the string. Okay, so you should have found with your string that we have 6 and then just a little extra. Okay, and so no matter what size circle, that will always be true. I'm going to go ahead and again show you some other size circles. So there's this one right here. Going around, we have 1, 2, 3, 4, 5, 6, and then a little extra. Same thing with this circle. We have 6 and then a little extra. We do a smaller circle, there's the 6th one and then a little extra. If we go bigger, here's the 5, 6, And then again, a little bit of space there. And we can also go even smaller, and that same thing will happen. That piece of string fits all the way around 6 times, and then a little extra. Okay, so going back to our worksheet, it says how many radius lengths rotate along the circumference of our circle. So it's just a little more than 6 radius lengths. Okay, and then the question is, why did you get that result? So one of the things you may remember from earlier math classes is that if we take the circumference of a circle, that is equivalent to 2 pi r. And if we think about that, the 2 pi, well, pi is 3.14. If we double that, we get 6.28 radius. And so if we go back to our idea of this circle, every time we put the string along here, we were going across, or we were going around the circumference of the circle, and we did it a full 6 times plus a little extra. And so we're taking our radius length and we're going around the circle a little more than 6 times to get our circumference. Okay, this angle right here is known as 1 radian length. And so that's what a radian is. It's taking the radius of our circle and then taking that same length and putting it around the circumference. Okay, so when we put it here, this is known as the radius. So radius. And then when we take that same length and put it on the circumference, and we get this openness, that's referred to as a radian, radian. Okay, what I want you to do next is take a look at number 2. We want to represent the following angles on the given circle. So if you have a piece of string that you can use, go ahead and kind of just measure it out, maybe with like a finger. You can use a shoelace, whatever you need. And then I want you to measure those. So take that piece of string, find where 1 radian is, find where 2 radians is, etc. So go ahead and pause the video while you complete this task. All right, I have the solutions on here, and they don't have to be super perfect, but they should be in the general area. So about 1 radian is in that first quadrant, so right here. 2 radians should be past that 12 o'clock position. I know it didn't ask for 3, but I did mark it on here. It should have been just shy of that 9 o'clock position. And then 3.5 is going to be after that 9 o'clock position. And then the pi, which is going to be 3.14, should be exactly at that 9 o'clock position. And that makes sense because if we go around the entire circle, that is 2 pi. So if we're going just pi, that should be halfway around the circle. We're going to be looking at the relationship between radians and degrees. So you may have seen conversions back in middle school. So we may have seen a problem something like, if you have 2.5 feet, how many inches would that be? Well, just a quick refresher, you multiply it by the fraction of, we want to be able to cancel our feet, so we're going to put 1 foot in the bottom and then 12 inches on top. So the idea is that this fraction right here is really just a value of 1. So we're taking 2.5 feet multiplied by 1, right? Because the numerator and the denominator are equivalent to each other. So now the feet are going to cancel, and then we're going to take 2.5 and multiply it by 12, which gives us 30. And then we are left with the unit of inches. So that is how you saw conversions back in middle school. Well, that same idea is going to apply here in the trig. So we're going to take our first problem. If we have an angle that has a measure of 70 degrees, what is the radian measure of that angle? Okay, so we're going to take our 70 degrees. And then again, we're going to multiply it by 1. So I'm going to start with the fraction, and this fraction needs to be a value of 1, meaning what's in the numerator has to be equivalent to what's in the denominator. Because we have the degrees in the numerator on that first part, so 70 degrees, we want degrees to be in our denominator, so it can cancel. And then the equivalent for degrees to radians is that 180 degrees is equivalent to pi radians. You technically could also use 2 pi radians over 360 degrees because that completes one full circle. That also works with conversions. You just have to end up reducing your fraction. All right, so now the degrees are going to go ahead and cancel. So we are left with 70 pi over 180 radians. And then we can plug that into our calculator. We're literally going to take 70 and then multiply it by the pi button, and then take that answer and divide by 180, and that gives us 1.22 radians. That means that 70 degrees is equivalent to 1.22 radians. All right, let's go ahead and convert in the other direction. So if we have an angle that measures 1.5 radians, what is the degree? Okay, so we're going to start with our 1.5 radians. Again, we want to multiply it by a value of 1, so what's in the numerator must be equivalent to what's in the denominator. Notice now that we are starting with radians, so in order to cancel it, the radians has to be in the denominator. Therefore, the degrees is going to be in the numerator. Okay, and so it's that equivalent value up on top, so 180 degrees is equivalent to pi radians. So now the radians are going to go ahead and cancel. So now we have 1.5 multiplied by 180 divided by pi degrees. And again, we can plug that into the calculator, so 1.5, multiply it by 180, take that answer and divide it by pi, which gives us 85.9 degrees. So that means that 1.5 radians is equivalent to 85.9 degrees. All right, so I want you to practice some of those conversions on your own. So I want you in just a second to pause the video and work through problems 4 and 5. You'll notice that all of problem 4 is converting from radians to degrees. And then on problem 5, it's converting all degrees into radians. Okay, so go ahead and pause the video and work those two problems. For problem 4a, you can see that we took 2 pi, multiplied it by 180, divided by pi, and that reduces to 360. And so if you think about it, 2 pi gives us 1 full revolution, which is the same as 360 degrees is 1 full revolution. Part B, we have 2.7 radians. That gives us 154.7 degrees. Part C, 4 radians, gives us 229.18 degrees. And then part D, pi over 2 gives us 90 degrees. All right, and then number 5, we're converting from degrees to radians. So 52 degrees gives us 0.91 radians. 90 degrees gives us pi over 2, or 1.57 radians. Part C, 243 degrees is 4.241 radians. And then part D, 270 degrees is 4.71 radians. Okay, so we're going to be using some of those values to create this circle right here. Okay, so it says label all x and y intercepts in both degrees and radians. And then notice in the radians, we want both the pi and the decimal form. Okay, so we're going to get lots of information with this circle. Okay, so we're going to start at our 3 o'clock position. So starting off, we're going to be at 0 degrees, which would be 0 radians. Next, let's stop at our 12 o'clock position. So I like to talk about the degrees first because that's what most students are familiar with. So at the 12 o'clock position, we have gone a total of 90 degrees. And then with that 90 degrees, if we look at problem 4, part D, you will see that 90 degrees is equivalent to pi over 2 radians. And if we actually take the 3.14 and divide it by 2, we get 1.57 radians. Okay, so anytime we're talking about that 12 o'clock position, we can refer to it as any three of those values. So we can say 90 degrees, pi over 2 radians, or 1.57 radians. Let's move on to our 9 o'clock position. We'll start with the degrees. So notice that's halfway around the circle. So that would be 180 degrees. We also discovered in problem 1 that one full rotation around the circle gives us 6.28 radians. So halfway around the circle would give us 3.14 radians. And you recognize that as pi. So that position gives us 180 degrees, or pi radians, or 3.14 radians. All right, let's go to our 6 o'clock position. So this one, 3/4 of a way around the circle is 270 degrees. From problem 5D, if we reduce our work there, we get 3 pi over 2 radians, which if you think about it, that actually makes sense if you think about our circle. We know that 90 degrees was pi over 2, and so to get to our 270 degrees, that is 3 sections of pi over 2. So that's why we end up with 3 pi over 2. All right, and then if we plug that into the calculator and reduce that decimal, we get 4.71 radians. Okay, so all three of those are equivalent values for that 6 o'clock position. All right, and then let's go ahead and wrap it up by getting back to our 3 o'clock position. So one full rotation would be 360 degrees. It would also be 2 pi radians. And then that is equivalent decimal of 6.28 radians. These values are very important. I recommend putting them on a note card and studying them. So if you see pi over 2, you immediately know that that's 1.57 radians. Or if you see 3 pi over 2, you immediately should know that that's 4.71 radians. So put these on a note card and study them so that way you have those values immediately available to you.